When evaluating converting a hydraulic cylinder to an electromechanical alternative, the first step in fully understanding the needs of an equivalent solution is to understand the amount of work that is being done. In general terms, this is a function of the area of the cylinder and oil pressure. It is very common to simplify this by using the piston area and maximum system pressure. Unfortunately, this will almost certainly lead to oversizing the system, resulting in significant increases in cost and size of the actuator. A more accurate way to determine the work and forces required is to understand the dynamic pressures during a process and then calculate the work, or thrust, by eliminating usable surface area of the cylinder rod and any pressure that is resulting from return line pressure. Using the back pressure and load simulator shown here, we can simulate work or load by restricting the flow going out of the cylinder. This restriction would be the same as any resistance created by tooling or required thrust in a process. As you can see, we can create the same force or load in either direction. The same can be done with the powered cylinder, which would simulate the component in the process that would be replaced with the electric actuator. With this cylinder, the restriction would simulate varying degrees of return line pressure either between the cylinder and the valve, or the valve and the reservoir. In many circuits, there will be very little return line pressure. However, in a circuit that would, for instance, use a servo hydraulic valve, return pressures between the cylinder and that valve can be quite high and must be accounted for to avoid improperly determining the required thrust. In this video, we will demonstrate both scenarios, one with high and one with low return line pressure. We'll first start with a low return line pressure. When looking for a place to measure these pressures, the optimal location would be at the cylinder itself to be as close to the point of work as possible. But it may not be possible to tap into the cylinder without risking replumbing of hoses and messy leaks. In this case, the next best area is to take the measurements at the valve. There may be some air moving back to the valve, but it is more conservative making sure that the pressure measurements are not underestimated. Even if you can only measure pressure back at the valve, understanding the work port and return line pressures will still be much more accurate than using rated system pressures. When measuring these pressures, we recommend using a smartphone or other mobile device to record the pressures on the gauge in both the extend and retract directions. The goal being to have a video of each gauge during the whole process. The video gives a means of viewing the pressure fluctuations that are found in many hydraulic processes and to more accurately see the true maximum pressure without pressure spikes. Having a video also gives you a recorded time of the process, which will be used later on in the process. Now, let's run through the exercise and capture some information using the test circuit shown here. As you can see, we have created a load on what I'll call our resistance cylinder. As the cylinder extends, you'll see we have pressure to extend the cylinder against our simulated load and also back pressure as the oil leaves the cylinder and returns ultimately to our reservoir. You likely have noticed that we have a slight delay when the cylinder begins motion and when the gauge starts to show pressure. This is a great example of what could happen when measuring pressure in the field and capturing your pressure readings on video. Now, we will repeat the process when retracting the cylinder. Notice again that we have set our return pressures for both sides of the cylinder to the same value to again replicate what would be experienced from oil returning to the valve. After reviewing the video, we have determined that the extend pressure was 401 psi and the return line pressure was 132 psi. Rather than assuming equal surface area on each side of the cylinder and simply subtracting extend pressure from return line pressure, we must take into account the force on each side of the cylinder, as we have unequal areas due to the loss of effective surface area caused by the presence of a cylinder rod. In this instance here, we have an 1.5 inch bore or piston diameter and a 3/4 inch diameter piston rod. Calculating the extend force is done by simply multiplying the piston area and pressures as shown. In this case, that force is 706 pounds. Please note that values may vary depending on the rounding used in your calculations. For the force on the rod end, we must calculate the rod's surface area, then subtract the piston surface area from that rod area before multiplying it by our measured return line pressure as shown. The resulting force on the rod end is 174 pounds. Now that we have both forces calculated, the calculated thrust required to move our simulated load is the difference between these two values, which in this exercise is 532 pounds. In the case of a low back pressure on the return line, this lack of resistance within the driving cylinder has a significant impact on your calculated thrust requirement from the same load. As we extend the cylinder, note now we have virtually no back pressure in our return line. This too affects the pressure required to extend our cylinder when the resistance of our load cylinder is remained unchanged. The same is noted during the retracting of the cylinder. Now, using these new pressures, when looking at the extend process, the resulting difference in pressures indicates that we now see a difference of 174 pounds of thrust between the two scenarios. You now see why measuring return line pressure and calculating force using the effective surface area is essential for accurately determining thrust. Finally, let's take and compare these two results with the common method of piston area and rated system pressure. Even assuming that the max system pressure is very close to what we measured, for example 750 psi, our resultant thrust requirement is 1,325 pounds of thrust versus 532 pounds and 706 pounds of thrust respectively. These equate out to a 60% and 47% decrease in thrust over the max rated system pressure method. As this relates to sizing electric actuators, even a 20% error in thrust calculation can have a significant impact on the price and size of the final actuator solution. We hope this video has been informative and will provide a starting point to help you as you evaluate a hydraulic cylinder to electric actuator conversion. In addition to this video, we have a complete education page designated to cover many of the different topics and questions surrounding converting hydraulics to electric actuators. Tolomatic also has a team of experienced application engineers and regional sales managers to further assist you with converting hydraulics to electric actuators. For more information, visit our website at www.tolomatic.com or give us a call at 1-800-328-2174 and let us know what we can do to help solve your linear motion needs.